Hi, good morning. Welcome to this presentation on fixed priority scheduling and controller code design for time-sensitive networks. My name is Xiaotian. I'm a member of the Real-Time System Research Group at the University of York. So the Real-Time System Group is an active and influenced research group in real-time system research in the UK. I got my PhD degree in the Real-Time System Group in Computer Science in 2019. And my research interests including scheduling in multi-cores and real-time networks, adaptive scheduling of cyber-physical systems, control scheduling and code design, and also safety assurance of autonomous systems. Before we start, I just want to give you some background on time-sensitive networks. For safety-critical systems, there are stringent requirements on safety, availability, and reliability for the system assurance purpose. And the communication in safety-critical systems that can provide determinism and predictability is very important for achieving such goals. Traditionally, real-time communication is achieved by using customized or non-standard protocols, such as a modified Ethernet. And some examples of real-time communication includes control area network and FLAG3 in the automotive industry, the AFDX Adrenic 664 for avionics, Model-bus, SICOS, Profibus, ControlNet, DeviceNet in the industry field bus, and also ICCAD, Ethernet IP, Perfinet, and PowerLink in the industry Ethernet. However, there are some challenges for these real-time communication protocols. So the first one is the sustainability is challenged by the emerging applications, for example, autonomous driving and smart city. Also, the nature of mid-criticality traffics are required to be transmitted and sharing the same hardware link, in which case the temporal isolation becomes essential. And also, in addition to the low latency requirement, there's also high data volume. Although the existence of different protocols in the same network results in increased cost of product and maintenance, and also increased difficulties in the safety verification process, thus the interchangeability between protocols becomes poor, and also bridges and routers are needed between two types of networks, and also the end devices must be compatible by increasing the redundant routines and software in the software design. To deal with the case, IEEE announced the 802.1 standard, the time-sensitive networking, or TSN, for real-time and time-sensitive network applications. So the TSN is developed by the Time-Sensitive Networking Task Group under the IEEE 802.1 working group. So the TSN consists of a set of protocols, which include 802.1 QB-Way for time-aware shipping, 802.1 QBU for frame preemption, 802.1 QCA for path control and reservation, and 802.1 CB for frame replication and elimination, and so on. So the TSN supports standardized connectivity and provides mechanism for traffic shaping and also traffic control. Among these protocols, the 802.1 QB-Way is recognized as the most important protocol and contributed to the real-time network scheduling. So here is an overview of a time-sensitive networking and topology. So there are a few number of components, which are the TSN and stations, the TSN-enabled switches, and also centralized user and network configurations. And here we define a packet as an entity to be transmitted over the network, and also the flow as a sequence of packets from a talker to a listener. When we have a look inside a TSN QB-Way switch, there is scheduled queues, which has 8 scheduled FIFO queues, and also a gate control list, which triggers the gate open and the gate close event periodically with a control cycle. The schedule is stored in a lookup table, and the conflicts are resolved by the priority selection module before sending to the XGrass port. A global timer is used to synchronize all the devices within a TSN network as well. The main contributions of this work is we convert the GC-air scheduling problem into a fixed priority scheduling under the IEEE 802.1 QBV standard. We propose a fine-grained response time analysis based on the schedule at the frame level. And also, we propose a control scheduling code design which achieves timing predictability and also maximize the control performance. In terms of the scheduling model, we have two types of packets, the control packets and non-control packets. We assume that control packets have implicitly deadlines, means a deadline equals to period. And non-control packets has the arbitrary deadlines, means the deadlines can be larger than the period. We also assume that packets are released periodically. So packet is modeled as a tuple, which includes the length of the packet, the transmission time, the period, deadline, priority, worst case latency, and also the frames. So we assume that the packets are scheduled offline using non-preemptive fixed priority scheduling, and priorities are assigned with deadline monotonic. This offline schedule will then maps and be encoded into the GC-air table, which will be executed at runtime in the switch or in the end station. In order to guarantee strict priority, the in-queues of early arrived packets will be deferred to avoid blocking according to the schedule. So for the response time analysis, we can say that the worst case transmission latency consists of three major parts. The first is the in-queue time, which is time duration from the packet enters the QBV switch to the time when it is in-queued. And the second part is the queuing delay, which is the queuing delay the packets gonna incur inside the FIFO queues. And finally, it's the transmission time, which is the time for transmitting a packet once it is being selected for transmission. So our response time analysis is performed at the frame level and providing a fine-grained timing bound towards network packets. For a given packet, its response time is bounded by the max response time among all its subsequent frames in one release. And in the following equation, we can see that the Ig gives the response time of the nth instant time and during the tau I speed period. For control packet, the n is equals to 0 for all its frames because it has implicit deadlines, so the packet could not be larger than 1. And for non-control packet, the n is computed based on the busy period Ti. Then we can have the response time equals to the in-queuing time of all the frames that have priority to the tau Ig, and the waiting time of tau Ig inside the FIFO queue. So this will be further decomposed in the following slides. And the Cig, which is the time for transmitting nominal Ig once it is selected. Finally, it's a arrival time of the nth instance, and resume the start of the busy period to be time 0. The queuing delay of frame nominal Ig can be formed by 5 delay sources. The first is the delay introduced by low priority frame. Because the schedule is non-preemptive, And so any packet has to be wait for that low priority frame to be finished. And the second part is the delay by previous instance of lambda IG during the busy period. And then the third part is delay by frames of tau I prior to lambda IG during TEI. The fourth part is the delay by the frames of tau I after lambda IG within the busy period. And finally is the interference for frames of each packet with a high priority. And on top of the schedule and the response time analysis, we also design a control and scheduling code design. The objective is to design controllers on a TSN network, which satisfy the control performance requirements and also under the schedulability constraint. In this work, the control performance is evaluated by the widely used metric, settling time, which is the time taken for a controller to experience a disturbance to the time it settles itself, which means within the 5% to the target. When we're designing a digital controller, both the period and the pause need to be decided. And for the period, as it will affect the schedulability of the network. So if a control packet is sent more frequently, it will use more bandwidth and makes it more difficult for other packets to fit into that schedule. And also for the pause placement, it is also desirable because the dynamics gonna be affected by the location of the pause. So these pause need to be placed carefully according to the designed engine values. The overall optimization problem can be formulated as follows. So the objective is to minimize the control cost, which is a weighted sum of all the costs of the controllers. And this is subject to the timing requirements. And the first one is the response time should be less than the period. And also the settling time, TSG, should be less than the maximum allowed value. As well as the control signal is also threshold by value. So this optimization problem can be further decomposed into two subproblems. The first is period selection, and second is probe placement. So for the first problem, we can use exhaustive search. As for network scheduling, the candidate periods are often limited, in order to be harmonic. For the second problem, we use particle swarm optimization, or PSO, to find the optimal pause that could produce the best settling time. And this algorithm shows the pseudocode of the period and pause assignment problem. So the first step is to initialize the whole solution space to find all the feasible solutions. And second step is to find all the candidate solutions by using the PSO search. And finally, we're going to return and find the best solution, which means going to have the least cost. As for the evaluation, we use MATLAB 2019B with the optimization and control toolbox. We have the following parameters set in which the network speed is 100 megabits per second. And the in-queue latency is the transmission time divided by 100 microseconds. The maximum transmission time of a control packet is set to be 120 microseconds. The deadline of control packets equal to period, which means D equals to T. And for non-control packets, they are generated using uUnifast with randomly generated utilization. And the period is randomly generated by using a set of harmonic period. We also make the code public, available on GitHub. As for the evaluation, we first evaluate the schedulability with a concrete example given in table 2. From the table, we can see that the response time, Ri, is less than deadline, which means all the packets are schedulable. To make a comparison, we compile the proposed method with a queue-level scheduling and with a random policy, and queue-level scheduling with deadline monotonic scheduling, and compile the schedulability indexed by phi, which is defined as the number of schedulable packets divide the number of total packets. And the error, and in the table, for example, the R10 means the network is lightly loaded, and M stand for medium loaded case, and H stand for heavily loaded case. And the number stand for the number of packets within that network. In terms of the control performance, we can say from the figure that from the figure 2 that the y-axis is a percentage of schedulable packet sets in regards to the network, in regards to the totally network workload of non-control packets. We can see that as the network load increases, the percentage of the feasible solutions drops quadratically, but it still holds at a reasonable level, which is around 30%, when the network load for non-control packets is 95%. And from the right-hand side, we have a figure that showing the control cost, showing the normalized control cost in regards to the total network load for non-control packets. And the worst case control cost increased dramatically. However, from the diagram, we can see that the minimal and average increase much slower than the maximum value, which means the a relative good control period and pause can still be found with the optimization solver, even the network workload is high. As conclusions, in this work, we have proposed a preliminary work on control and network call scheduling design on TSN network. And we proposed a response time analysis for the proposed schedule with the consideration of multi-frames and unconstrained deadlines. We also proposed an optimization method to select control task period and the control pause. This work can be extended in a number of ways. And the first one, which is also an ongoing work, is to support non-periodic traffic, for example, sporadic and periodic traffic using utilization, using bandwidth reservation. And the second direction is the exploration of dependability, which means the scheduling of flows with dependability that is modeled, for example, using direct acyclic graph. Finally, is to extend the scheduling model and the analysis to the topology level that could scale with a large number of switches and stations. That's all for the presentation. Thank you so much. If you have any questions, please ask during the live section.